Okay, we're going to talk about tutorial 5 on tension. This tutorial I sometimes call the mother of all tutorials. If you were doing this in person with a number of your classmates, there's a greater chance of you crying during this tutorial than any other tutorial. We'll try not to put you through that. Let's share my screen. Okay. Now, we start with two blocks that are connected by a heavy rope, and the hand is pushing on the smaller block, and the table here is frictionless. And so the first question we're asked is, what's the motion going to be like? What are these blocks going to do? Well, we know that if we have a frictionless surface, if we keep pushing on something, it speeds up, it accelerates. And so I would say they all accelerate to the right with equal acceleration. Okay, it's got to be equal because they're moving as a unit. They're moving as a unit. Now, we're asked to draw free body diagrams for A, B, and C. And what I'd like you to do is pause the video right here and get out a piece of paper and draw those free body diagrams. Just don't go further in the tutorial video without hitting the pause button and drawing your own uh, free body diagrams. I'll wait. Okay, you must be back. So let's do them together. If I pretend that I'm you, I know that statistically there is a very high probability that what you did for A is you put weight down, earth pulling on A, and the normal by the table up on A. And if you did the same thing for B, you'd just have a smaller weight and a smaller normal force. And we also know that the rope is pulling with a tension force on A, and that means that A must be pulling with a tension force on the rope. And we also know that the rope is pulling back on B, and so I must have a third law companion of B pulling on the rope. And if I were working with you on this tutorial, if I were there in your study area, I would remind you that this is a heavy rope and that this rope, this is B and this is the rope, this rope has a weight. And then I would remind you that we just said that the whole system was accelerating to the right. And that diagram screams to the right. So bravo. this one doesn't scream to the right, and that's because I'm missing a force. I forgot to put the normal force by the hand on B, and so now this diagram screams to the right. But this diagram doesn't scream to the right. And you might be tempted to fix that by just making that force a little bit longer. But then there's this downward force, and that needs to be somehow balanced. And if you were to try to balance that with some other force, if I were in your study space, I would challenge you to label that force. What's causing that force? What boogeyman could you blame that force on? And as a general rule, if you can't find the boogeyman to blame the force on, that force just doesn't exist. So let's fix that. Let's draw a free body diagram for block A. I have a weight force and a normal force. But I notice that where the rope is attached to A, there's some sag. And that's going to be true if I have a heavy rope and if I'm on a frictionless um, surface, the table. And a rope can only pull in the direction of the rope. And so that means that my force, the tension force by the rope on A, has to be in the direction of the rope, which would be down. And I can think of that as having two components, a horizontal part and a vertical part. Now, because that vertical part is down and the weight is down, that means my normal force has to balance both of those. And so that means that the normal force by the table on A is going to be greater than the gravitational force on A. Now, if I draw the free body diagram for the rope, I have that weight force acting on the rope. And by third law, if the rope is pulling down and to the right on A, then A is pulling up and to the left on the rope. And those are third law companions. And again, I can break that up into its components like that. Now, I also have for B, a weight down and a normal up. And the hand pushing. And again, the rope is sagged there, and so I'm going to have a tension force by the rope on B that is down and to the left. I can think of that as components. And by third law, if the rope is pulling down and to the left on B, then B would be pulling up and to the right on the rope. And I would put 2 tick marks there to indicate that those are third law companions. And again, I can break this up into its components. And now you see that this weight force, the gravitational force on the rope, is supported by these upward components of the tension. And so now this diagram screams to the right as long as this horizontal component is bigger than this horizontal component. And this diagram screams to the right as long as the force by the hand is bigger than this horizontal component. And of course, the diagram for A screams to the right, regardless, because there's no friction on this table. And this is confirmation that the whole system is accelerating to the right. If block A is accelerating to the right, its diagram screams to the right. And if they're all moving together, then these guys must have free body diagrams that scream to the right as well. Again, because I have a downward component of this tension force, my normal force by the table on block B has to balance both this downward component and the weight. So again, the normal by the table is going to be greater than the weight. Now, if we want to rank from largest to smallest the magnitudes of the horizontal components of the forces, well, I know that the normal by the hand on B has to be greater than the tension by the rope on B, the X component. Whoops, okay, there we go. Why do I know that? Because B is accelerating to the right. I know that this has to be greater than the tension by the rope. I'm sorry, oh, my bad. We want all the horizontal components. So this has to be equal to the tension by B on the rope, the X component, and this is by third law. And this has to be greater than the tension A on the rope, again, the X component. And this is because the rope is accelerating to the right. And that has to equal the tension by the rope on A, the X component. And that's by third law. Now, I want to point something out. This tutorial claims it's about tension. And indeed, we're going to learn some things about tension here. But mostly this tutorial is an excuse for practicing Newton's second and third law. And so that's what I really want you to get out of this experience is when do you use Newton's second law? When do you use Newton's third law? Whenever I'm comparing two forces that are acting on the same dot, on the same free body diagram, I'm using Newton's second law, okay? And whenever you use Newton's second law, you have to, qualify it. This horizontal component has to be bigger than this horizontal component by Newton's second law with acceleration to the right. Since there's acceleration to the right, my diagram has to scream to the right. I've only got one force to the right, one force to the left. The force to the right has to be bigger than the force to the left. Let's finish this page up. Consider the horizontal components of the forces exerted on the rope by blocks A and B. Is your answer above for the relative magnitudes of these components consistent with your knowledge of the net force on the rope? Yes, indeedy. We just talked about that. Okay. Now we're going to do something that really, really, really looks like calculus, but it's really, really not. Okay. We're just going to call it magic instead. Okay. We're going to wave a magic wand and suddenly transform that heavy rope into a light string. But we're going to do it in such a way that the motion of the blocks is the same as it was before in section 1. Now, when I say motion, what I really mean is acceleration. If the acceleration before was, I'm making this number up, 3 meters per second squared, we're going to push on this frictionless table in such a way that the acceleration is still going to be 3 meters per second squared. Now, what does that tell you about the push by the hand? Well, overall, I have less mass than I had before because the string doesn't have as much mass as the rope. A and B are still the same, but the string is less massive than the rope. And if I want to give that smaller, less massive system the same acceleration, then I'm not going to need to push as hard with the hand. And so that force is going to get smaller. So that means that the net force on the string, which equals the mass of the string times A, is going to be less than the net force on the rope, which is equal to the mass of the rope times A. The A is the same, but the mass of the rope is bigger than the mass of the string. Now, then determine whether the net force on each of these objects is greater than, less than, or equal to the net force on the object in section 1. Well, if I look at block A, the net force on A is equal to the mass of A times the acceleration of A, and that's the same. I didn't change the mass of A, and I didn't change the acceleration of A, so I have the same net force. Likewise, the net force on B, the mass of B times the acceleration of B, that's going to be the same for the same reasoning. The mass of B didn't change, the acceleration of B did not change. But the system that is comprised of both the blocks and the connecting either rope or string, that is going to be different. And we just talked about that. The net force, because the net force on the string is less than the net force on the rope, the net force on the new system is going to be less than the net force on the old. Okay. Now, in this part, we want to compare just the horizontal components of the following pairs of forces. The force on the string by block A and the force on the rope by block A. Well, which forces are those? We're looking at this force right here. This is A on the rope, and we're saying, how does this change if we magically wave our wand and turn this rope into a string? Well, first of all, we need to know that the tension by the string, I'm sorry, the tension by A on the string is equal to the tension by the string on A. Okay, and I'm just looking at the X components. Well, how do I justify that equal sign there? Well, notice that I've got the same indices, A pulling on the string versus string pulling on A. And that's going to equal the net force on A, right? Well, what do you mean, Greg? What I mean is that this force here, that's A on the rope, think of it now as a string, uh, is a third law companion to this force here. But this force here is the unbalanced force. That's what's causing the acceleration of block A, because the normal force up balances these two forces down, and this is all that's left. That's the net force right there. And so if the net force on block A doesn't change, it stays the same, then this is going to equal the tension force by the rope on A in the X direction, which is equal to the tension by A on the rope, the X component. So what we're saying with all of those equal signs is that this force right here can't change. And hence, this force can't change. Okay. And again, the reasoning is by Newton's second law. If the mass of block A doesn't change and the acceleration stays 3 meters per second squared, then the net force, that's this right here, has to stay the same. And if this stays the same, so does this by Newton's third law. Okay? Now, what about the force on the string by block B and the force on the rope by block B? Well, if I look at this connecting object, which starts out a rope and changes to a string, I don't need as much force to accelerate a string, a little tiny string, as I do to accelerate a massive rope. And so what I would say is that the tension by B on the string is going to be less than the tension by on B by B on the string is going to be less than the tension by B on the rope. Okay, and that's because I need more net force to accelerate the rope. Suppose that we make this string less and less massive. The mass of the string becomes smaller and smaller and smaller. It becomes heavy twine, and then it's a thin piece of thread, and then it's the dental floss that you never use. It's getting smaller and smaller. And then since the net force is equal to the mass times the acceleration, and we're told that the motion stays the same, which means the acceleration stays the same, but the mass is getting smaller. Well, that means that the net force gets smaller. But if we look at the individual forces that are acting on that string by blocks A and B, it doesn't mean that they're getting smaller. Indeed, we found up here that the force exerted by the string on A has to stay the same. And hence, the force exerted by A on the string, which is a third law companion to this force, must also stay the same. But I don't need as much net force on this string as it gets smaller and smaller. And so that means that this force by B on the string must become closer and closer to whatever I have here. Okay, I'm going to put some numbers here. If this was 5 newtons, and this is 5 newtons, and this is 8 newtons, and that's 8 newtons, and let's say that this is 12 newtons, well, that's for a heavy rope. When I change this to a light string, I still need 5 newtons here, and I still need 5 newtons there. But for a light string, maybe I only need 6 newtons here. Now I still need the same net force over here. I had 12 minus 8 or 4, so now this is going to change to 10 newtons. And if I let this string get smaller and smaller and smaller, eventually I won't need any net force at all. And this will turn into 5 newtons. This will turn into 5 newtons. And this will turn into 9 newtons. Okay. So, so the tension force by B on the string gets smaller, approaching the tension by A on the string. They become similar in magnitude. A string exerts a force on each of the two objects to which it is attached. For a massless string, the magnitude of both forces is often referred to as the tension in the string, a single quantity, a single number. Justify the use of this approach, in which a single value is assumed for the magnitude of both forces. Well, by Newton's second law, and that's usually the way we reason these things, if the mass goes to 0, we don't care what the acceleration is. It can be huge, okay? If the mass is 0, the net force must also be 0. And so that means that if I draw a free body diagram for a massless string, first it's boring because I'm going to have forces on both sides that are equal to each other. Okay? Because it's got that diagram has to scream balance. It has to scream 0. Okay? Now, the second thing about a free body diagram for a massless string is that it's confusing because we've taught ourselves that the free body diagram should always scream the acceleration. And since I have an acceleration to the right for that string, I expect my free body diagram to scream to the right. But because of this quirk of mathematics, it always screams balance. And so I would encourage you from now on to never draw a free body diagram for a massless string. It's not going to give you any information that's useful, and it will just confuse you. Okay? Just don't do it. Don't do it. Okay, if you know that the net force on a massless string is zero, what, if anything, can you infer about its motion? Absolutely nothing. We just talked about that. Is it possible to exert a non-zero force on a massless string? Yes. Is it possible for a massless string to have a non-zero net force? No. Okay, again, I can have a tension force by B on the string equal to 1,000 newtons, as long as I have a tension force the other way by A on the string that's also 1,000 newtons. I can exert non-zero forces on the string, but I can't have a non-zero net force. Okay, the net force has to be zero. I'll discuss the answers with myself. Okay, I'm done. Now we're going to look at an Atwood's machine. An Atwood's machine is just two blocks connected by a massless string hanging over a pulley. And what we find is that in every introductory textbook, we have problems involving the Atwood's machine. And indeed, we often find problems involving an Atwood's machine on the MCAT exam. So we originally hold object B in place such that it's above A. And both of these masses are the same, 200 grams. And we let go, and I hope you can see that they go nowhere. Okay, they go nowhere. And if I draw free body diagrams for A and B, if we were on the that planet where G was exactly 10.0 newtons for each kilogram, then this would equal 0.2 kilograms. This would equal 0.2 kilograms. And if I multiplied that by 10, that would give me a weight force equal to 2 newtons. Okay. Now, since these are not going anywhere, they're balanced, my tension force by the string on A has to be also 2 newtons, and the tension force by the string on B would also be 2 newtons. But now we have a different situation. We have 200 grams and 400 grams. And your gut tells you what's going to happen. I've got more weight over here than I have over here. And so this is not going to stay balanced. C is going to accelerate downward, and A is going to accelerate upward. And because they're connected by a string that can't stretch, it's an inextensible string, it's not a bungee cord. If C goes down 3 inches, A goes up 3 inches. They're moving as a unit. And so if I had a speedometer on C and a speedometer on A, those speedometers would always read exactly the same number. And so that's why I can say that the acceleration of A is equal to the acceleration of C, but with a minus sign. They're equal in magnitude, but opposite in direction. That minus sign says that if A is up, C is in the negative up direction, which would be down. Okay. Now, if I draw free body diagrams for A and C, I would have a weight force of C, since it's 400 grams or 0.4 kilograms, that would be 4 newtons. And the weight force of A is 2 newtons. Okay. Now I know that A is accelerating upwards and C is accelerating downward. There's something else I know, and that is that the tension at the two ends of the same massless string has to always be the same value. And so that means my tension force by the string on A has to be something greater than 2 newtons. And I also know that that tension force by the string on C must be less than 4 newtons. Let me draw that 4 newtons a little longer there. Okay. And I also know from what we just learned in this tutorial that the tension by the string on A is equal to the tension by the string on C. And this would be by the law of massless strings. Now, you're not going to find that law in any physics book. That's just a law that I have named, but it's true. It's a true law. For a massless string, I've got the same pole at both ends of the string. Okay. Are the predictions you made in part C consistent? Yes, of course they are. I made them. So the weight of the 200-gram mass is 2 newtons. The weight of the 400-gram mass is 4 newtons. How does the force exerted on object A by the string compare to these two weights? String on A is going to be greater than 2 newtons. And the tension by the string on C is going to be less than 4 newtons. And because the tension is the same at both ends, that means that they have to be something in between 2 and 4 newtons. How does the net force on object A compare to the net force on object C? Well, the net force on A is equal to the mass of A times the acceleration of A. And that's going to be less than the mass of C, acceleration of C, which is the net force on C. Indeed, since C has twice the mass, it will have twice the net force. Consider the following statement about an Atwood's machine made by, let's call this student 1. All strings can do is transmit forces from other objects. That means that the string in the Atwood machine just transmits the weight of one block to the other. Well, what this student is saying is that if we draw our free body diagrams for A and C, where this is 2 newtons and this is 4 newtons, this student is saying that the string transfers the 4 newtons over here, and the string transmits the 2 newtons over here. Well, you know that this is wrong, and indeed sick and wrong, because the tension at the two ends of the string is not the same. But you can also show that it's wrong by Newton's second law. The net force here is 4 up minus 2 down, or 2 newtons up. The net force here I have 4 newtons down, 2 newtons up. That's going to equal 2 newtons down. Well, they have the same net force in magnitude. The direction's different. And they have the same acceleration. We said that before. Well, that means they have to have the same mass, but they don't. So this is wrong and sick and wrong. And student one is once again mistaken. Okay, that concludes the tutorial. We're going to stop our share and stop the recording.